Hello everyone, it's a great pleasure to have Ivonne Zavala here today. Thanks a lot for accepting our invitation. Ivonne is currently a faculty member in the physics department at Swansea University. She completed her PhD at the University of Cambridge and went on to hold postdoctoral positions at Durham University, University of Groningen, University of Bonn, before joining Swansea. She works at the interface of cosmology and string theory, spanning early and late universe dynamics, including single and multi-field inflation, string-motivated dark energy, multi-scalar cosmological models with theoretical consistency constraints. She also studies gravitational wave probes of the early universe and their detection prospects with LISA, the Einstein telescope, and pulsar timing arrays. Today, she will present scalar fields in string cosmology, dynamics, constraints, and challenges. Yvonne, please, you can start when you're ready.
Thanks very much for the invitation and everyone for joining. So today the talk will be a little bit more theoretical on my side. And what I want to discuss is scalar fields which abound in string theory in the context of string cosmology and focusing on the dynamics, what constraints we have, and some of the challenges that we face. And so the talk will be based on different works which I've been doing in the last years and in different collaborations. So I just want to thank my collaborators in these works. Oops. Okay, what's happening? Yeah. So, so as I was saying, scalar fields abound in string theory compactifications, where we start from 10 dimensions and, well, which we don't observe. So we have to go down to 4 dimensions only. And this process introduces plenty of scalars, which arise from the geometry, this geometry of the internal space that we are compactifying on, and also from higher dimensional generalizations of gauge fields, which are under the name of p-forms. So scalars are the simplest possibility to do cosmology. So in fact, such scalars that arise in string theory have been extensively used in the context of the early universe cosmology for inflation. And some also have been explored as in the context of cosmological tensions, such as early dark energy, and also now latent dark energy candidates. Also, I think people here are aware of axions, which again also descend from string theory in abundance, and some of them can be used as dark matter candidates very naturally. They can also arise as coupled scalar sectors. We know about the axiars and so on. So on the other hand, well, we are here because we know there are plenty of interesting results from the observational point of view, and in particular in the context of dark energy, the latest cosmological observations from last year and this year as well seem to be hinting at the possibility that dark energy today is maybe due to some dynamical form of dark energy. And of course, in this case, scalars may again be relevant. Now, on the other hand, from the more theoretical side, in the past years, there has been some activity in trying to constrain those theories that will be consistent with quantum gravity. And in particular, those ideas have led to the suggestion that perhaps a positive cosmological constant of de Sitter is inconsistent with a consistent theory of quantum gravity. Now, whether this is, so these are still some ideas that have no proof, but whether or not we take them as given, we may still wonder about what if a positive cosmological constant is indeed not possible to be realized. So we'll have on the theoretical side and on the observational side, we'll have hints that perhaps indeed the current expansion of the universe is maybe due to a dynamical form of dark energy. So what I want to discuss is how do we see this from the point of view of a string realization coming from in terms of scalars. And in particular, I want to focus on what I'm going to call the axion-axion system. So axions are very common, are well known. This axion name is inherited from supergravity. I will explain this. So I'll first introduce how these fields arise, and then focusing on each of them, this class of fields that arise from a string integral compactification, how we can use them to try and address, well, in the context of dark energy today. Then I will see what are the sort of the challenges and how some of these challenges take us to consider not just a single axion on its own or this axion on its own, but actually together as they actually come from a model. And in particular, why this will be interesting. And here the protagonist will be what I will call a non-geodesicity parameter, and we will see more what this means. If I have time, I will mention something about how we can see this also as a coupled, very naturally coupled dark sector, a scalar dark sector, but I will just mention a few words because we had a talk before in March by Elsa Teixeira, and she mentioned something, some of these ideas. And then I will conclude. Okay, so how do we see these scalar fields arising from string theory? So we start in 10 dimensions where the theory is well defined. We have to go down to 4 dimensions and write our low energy effective theory. So this process of try to hide, if you want, the extra 6 dimensions brings down 2 classes of scalars. Let me call them scalars, both of them, or moduli. So the first class is geometric moduli, which are associated to the geometry in which we are compactifying. Usually we use a specific type of geometry, Scalar-Gauss, but compactification can be simpler in terms of tori, for example. So these geometric moduli are the first class of scalars that arise, and usually they will be associated to some expansion parameter. The other class of moduli that arise are associated precisely to these higher dimensional p-forms, which are nothing more than generalizations of gauge fields, but in 10 dimensions. Now, these 2 classes of fields, of moduli, we usually package them together into pairs, and in particular into a complex scalar in the context of n=1 supergravity, where the geometric moduli in my convention here, these geometric moduli arise as the real parts of such complex scalars, while the imaginary parts are the axions. So the axions, again, these descend from these gauge, these p-forms, and therefore they inherit a shift symmetry. Now, this shift symmetry originally will be continuous, but then is usually broken by non-perturbative effects. We generate a potential and keep the symmetry only a discrete symmetry. This, however, the symmetry can be broken completely by other effects, and then we'll have also some breaking of this as well. Now, I can say that the most famous, axion system that many people or some people may have heard about is the axiodilaton. This indeed has been used also in the very old times of string cosmology, where indeed the axion here is associated to an expansion parameter, the string coupling. But okay, so, but in general, this is more general, and we can have many more pairs, if you want, of axion as complex scalars. So at the end, we want to write down our action in the n=1 supergravity language. I'm not going to go into detail here, but what I want to point down here is that the kinetic terms for those scalars are complex scalars in this language. The kinetic terms have a non-trivial form, and in particular have a coupling. So this here plays a role of metric in the manifold spanned by the scalars. So it's clearly non-trivial. On the other hand, the scalar potential is computed from some of the functions that we compute from the 10-dimensional perspective in terms of the superpotential and the Keller potential. And it has a non-trivial form, so it's clear that there is a non-trivial in general. The potential is not trivial, but it's also constrained. So there are, so the punchline here is that there are in general kinetic couplings and potential couplings arising from these pairs of scalars. So, but for cosmology, and just to extract what are the main features, we just want to write everything in terms of real fields. So this Lagrangian will be my starting point, where I may have two or more scalars. What I will be focusing on is one pair of these axion-saxion. So it's one axion and one saxion. And the main point is that there is a non-trivial field space metric. So field space, or the metric that is associated to the manifold spanned by the scalars themselves. And on the other hand, the potential is also going to include a coupling between the axion and the saxion. So this will be like the sort of starting point where we go. Okay, so we write down our action and we see that we have a potential, and this is where exactly the theoretical constraints come into play, because the suggestions or the ideas, the constraints that have been pointed out are associated to this potential. And what these people have been proposing is that, well, actually, it's maybe that I am in a consistent theory of quantum gravity, a positive cosmological constant cannot arise. So how is that translated into the scalar potential, which is the relevant object here? It's translated in the following form in constraints for the derivatives of the potential, the first derivative and the second derivatives. And so this basically is telling us that, well, the potential in general are going to be steep or very unstable. And in particular, this clearly is forbidding this kind of extrema for my potential. So here, just focus on a single scalar. But what these two conditions are implying is that it's not possible to have this kind of extrema, which will be like a positive cosmological constant when we focus here. On the other hand, having positive potentials of this form, which is what we call runaway de Sitters, satisfies if the derivatives are sufficiently large, then they will satisfy this constraint, so they are allowed. Or if they satisfy this constraint sufficiently unstable, then these de Sitter-like solutions will be possible. Okay, so again, these are still coming into the form of conjectures, but let's just take it for the moment and see where it takes us. So if we take it as face value, we say, well, these theoretical constraints and the recent data seem to be hinting, both of them, at the possibility that perhaps dark energy today is not due to a positive cosmological constant, which will be something like this if we think about the potential for a scalar, but rather it will be something of this form. So where the potential is positive, so positive cosmological constant, but there's a scalar field that is moving along this potential, or a situation where we may have this kind of potentials which are positive in this way. So, so this is kind of where we are moving, both from theory and observation. Dynamical dark energy. However, so when we consider dynamical dark energy, in particular driven by a scalar field. Here, let's focus for a moment on a single scalar field. Well, we can simply consider that the cosmological constant is 0. We're not solving the cosmological constant problem, which remains, and we have to remember that. And the other thing that we need to keep in mind is that quintessence, this type of models, whether it's coming from field theory or from string theory, these kind of models present several challenges from the fine-tuning point of view, because we know that the scale of dark energy today is very small, which, if this is due to a scalar field, quintessence, then implies that this field is very, very light. And we also have to worry about the initial condition for such a field. There are also associated phenomenological problems associated to forces, fundamental variation of fundamental constants, etc. So the idea here is that maybe if we try to use, let's say, the tools that come from string theory, maybe we are able to maybe not solve, but relax these problems or have some ideas how these challenges can be addressed. So that's one of the motivations, and I will comment on some ideas along these lines. Okay, oops, yeah. So we are driven to these two situations if we think about quintessence in the case of string theory setup. For runaway quintessence, the kind of stringy runaways, let me call them like this, usually arise out of this form, exponential. Now, this is very simple. It's just a single exponential. Runaways, stringy runaways can have a little bit more structure, exponential-like or other forms. And what we found also in this paper and also other people, what you can very quickly realize is that the moment you focus on single field, even if you consider more complicated kind of runaways, usually there seems to be, the potential seems to be too steep. And so more recently also, there has been a more concrete calculation of what will be the constraints on this parameter if we just consider a single exponential. And it was shown that from this Swampland constraint point of view, this parameter has to be larger or at most of order square root 2. So, so the idea now with the recent data from DESI from last year and this, the idea was to, so one of the things that we explored was to say, well, what maybe there are other possibilities, maybe the data now can tell us something more, but as we found, the parameter lambda here for this kind of potentials is less than square root 2. Now, this was already studied some time back before DESI results. And even if we include curvature, which is motivated also from string theory ideas, let me not get into the detail, but including curvature could be a way to get around this constraint. However, as we found, and also has been revisited with the most recent data, the punchline is that if you focus on this kind of potentials, the observational constraints give you values of lambda which are less than the required theoretical constraint. Okay, so we may discard that case, but we still have the option to look at hilltop quintessence. And so again, all these kind of models have been considered in the past for some reasons. So we wanted to focus more on what kind of hilltop quintessence within string theory we can have. Axions, again, have been studied in the past. So axions are more attractive because from the model building point of view, and in order to address some of the problems I was mentioning at the for some previous slides. They are more accessible thanks to this shift symmetry that they have. On the other hand, saxions themselves, which are moduli associated to the geometry, usually require a little bit more model building. The type of hilltop that you get also is different depending on which field you have. So it's a little bit more complex, but still one can work their way through this. So we explored these two types of hilltops with the data from last year. So in the case of axion quintessence, well, the potential is just a cosine, like so. So as I said, from the point of view of model building, is a little bit more promising. Here, one idea that we explore to realize this hilltop quintessence, the problem here, the initial condition will be, why do you start at the hilltop, right? So one idea that could be imagined in the context of these stringy axions was that in the early universe, the leading non-perturbative effects led you to the scalar to be at the minimum, whether this minimum is Minkowski or negative, so anti-de-Sitter, could be any of these possibilities. But the idea will be that later on, in the later universe, a little later, some subleading non-perturbative effect may kick in and turn the minimum into a max or nearby the Sitter maximum, and therefore this could be a potential way to sort of try to relax this initial condition for these stringy axions. We did not realize a concrete full model, but it was just an idea that we proposed. Now, in terms of constraints, this long time ago was suggested that this parameter here, this decay constant here, or the symmetry breaking parameter here, has to be of order Planck and not more, so sub-Planckian. So we explore also this in the context again of the data from last year, and it has been also revisited with the data from this year. And the punchline here is that the observations give value for this decay constant, which is, okay, of order n Planck. So this will mean, from the theoretical point of view, it will mean just that it's, as we say it, as at the border of being consistent, let's put it this way. So doesn't seem to work very, very well. And again, it's all because at the end of the day, we need a potential which is sufficiently flat. So for the saxions, we took a very specific supergravity axion in this case, and we just wanted to explore what happens with this type of models or moduli or scalars. From the point of view, again, of model building, it is a little bit more challenging to explain initial conditions. There are some ideas in terms of high temperature effects, but again, it's more complicated. We just explored this to see how the data from this, see what kind of values they will give for the involved parameters. Here, there's only one parameter, this constant alpha. The hilltop looks like so. And in this case, what we found is that the theoretical constraint will give us a range for this alpha in these values, while the observational constraints will give us a value very close to the border of this constraint. So again, we see that we are again at the limits of control in terms of this single field, either runaway or hilltops. So indeed, it seems single field quintessence for the type of scalars that we get in stringy setups are a little bit in conflict because data tell us that the potential has to be very flat, but the values that we get usually from our models are not the correct ones to have very flat potential. So this motivated, and actually motivated already some recently, the idea that is inherited from inflation, that, well, maybe if we don't consider the axion and this axion on their own, but actually as they come together as a pair, or more generally multi-field scenarios, perhaps one can address this issue because as it has been found in the context of inflation that you can have accelerating solutions even in the presence of very steep potentials, so long as you move along strongly non-geodesic trajectories. So this is what I would like to explore next. So, well, when can we have this kind of trajectories? When we have these systems of axion that come from stringy setups. So now I'm going to introduce this non-geodesic parameter. And this is, so the motivation comes from here. And basically, we are thinking about multi-field quintessence and explore if these ideas can be realized. Now, some of these, some models have been explored in the past years, and some of them have been focusing on multi-saxions, so only one class of multi-field models, or the other one, I think, as well. But also either consider just the pure kinetic coupling or just the pure potential coupling, or very specific cases that can be treated, let's say. In many of these examples, also the way to study these a little bit more complicated setups has been to use dynamical systems. So I don't want to give a full lecture what is a dynamical system, but I just want to say a few words why this is so, because why people use it is because this technique is very powerful in the context of cosmology, because it allows to understand a lot about the dynamics of cosmological models without actually solving or exploring blindly. And in this setup, you simply need to identify what are the suitable variables that allow you to rewrite your system as an autonomous system of first order differential equations rather than second order. And then you look at the phase space structure and analyze all the dynamics, and this already gives you a good idea of whether or not your model may be able to give you a realistic cosmology rather than going a little bit blind without knowing where to look. So that's why they are very useful. Here's a nice review from the 2017. So this is the techniques that I'm going to discuss next and how we studied this. And the idea, so again, the idea is to say, okay, now I know that the kind of models I'm going to have generically have a kinetic as well as a potential coupling. Now you very quickly realize that for these generic couplings, in the context of these dynamical systems, you run into problems to close the system, and also to identify what is the kinetic coupling doing on its own. So then the question of when these trajectories that we are looking for to address the issue of the requirement of a flat potential or accelerating solutions, when do they arise? When does these non-geodesic accelerating trajectories can arise and can actually also be attractors? So that's kind of the questions we wanted to answer in what we did next. So from now on, my protagonist, so I'm going to focus very explicitly. So this is the starting action. So in principle, it's this form. But I want to focus on this where I have a single pair of axion and a saxion. My axion has a shift symmetry, remember, so that's going to be chi in my notation, and phi is going to be my saxion. Kinetic coupling is there, and because the axion has a shift symmetry, the most general metric for the field space I can write has this form, so it depends only on the saxion. On the other hand, I'm going to choose this potential, which can be sort of resembled from a supergravity point of view and therefore a more stringy point of view, where I want to explicitly have this coupling between the axion and the saxion that will allow me to track, if you want, track what this potential coupling is doing. So in this way, I identify kinetic and potential coupling, and I want to find when I will have this kind of non-geodesic trajectories. Okay, so I want to look at the cosmology, and because we are thinking about dark energy today, so I have to include also some fluid, which is going to be, in general, we want to include matter because we want to see at the transition matter and dark energy today. So there's going to be a fluid plus the two scalars. These are the equations of motion, but for identifying these non-geodesic dynamics, it's more convenient to write the equations of motion in terms of projections along the tangent and normal directions along the cosmological trajectory. And the protagonist here is a parameter, this omega, in particular the dimensionless one, omega over h, which is measuring, as we see here, measuring how much I'm deviating from the geodesic in field space. Now this Vn is just the projection along the normal direction of the derivative of the potential. So obviously if there's a potential in general, it may be very small, but the moment is very large, that is going to give me a non-geodesic trajectory. And just to have, an expression in terms of the Lagrange, scalar Lagrangian I have, this is the form. So here, okay, it's just, I just wrote it down, I can do it, and it's given in this way. So the kinetic coupling appears here as well as the potential. So we'll come back to this in a moment. So just to have a more like pictorial idea of what we are looking for, what's the idea, is the following. So we want to look at trajectories that are really multi-field, and those are characterized by this parameter being larger than 1. So if we imagine that the potential has this kind of shape, a geodesic trajectory, so the potential may be very steep, so a geodesic trajectory will be one of the standard one that is just too steep to allow to satisfy the Swampland constraints, etc. And we are looking for trajectories of this form, which will be in this pictorial picture, a non-geodesic trajectory. So that's where we are trying to move and find when this can happen in the context of these models. So the next slides are going to be a little bit technical. So I just want to summarize how we did this in this work. So again, the starting point is this Lagrangian where I have my kinetic and my potential coupling. And we want to identify these trajectories when they can happen in this system. So what we did is to precisely identify what are the dynamical variables that are needed, not only to close the system, we again work with a dynamical system. So to close the system and also to allow us to disentangle the role of the kinetic coupling and allow us to study the full dynamics. Then we also found an expression for the protagonist, the non-geodesicity parameter, which is precisely the one that is going to tell us when we have these trajectories. And we also found non-geodesic fixed points, as we'll see, in the case where both the kinetic coupling and this potential coupling are exponentials. So this in few words. So now I'm going to go a little bit more detail. So here, for people who may be familiar with this, analyzing these scalar models with dynamical systems, we introduce the sort of the usual, let me call this way, dynamical variables that are associated to kinetic energies for the two, the axion and the suction, and potential energies as well, and then one associated to the fluid. There's a Friedman constraint. But if you just work with these variables, you very quickly realize that this does not close the system. So we need to introduce new variables. And two new variables are required for two reasons. So the first variable is required to close the system and disentangle the role of this kinetic coupling. But you will find very quickly as well that in order to be able to study the stability of the system, you also need to introduce a second variable. And this is the other variable that we need. So at this point, what we need is to rewrite the second order equations in terms of equations for these variables, as well as in principle equations for these parameters, which are associated to the various derivatives of the potentials and kinetic coupling. So in principle, there are, of course, many equations. Now here, before I go into a little bit more detail, let me just show the turning rate parameter is exactly the same. It's the non-geodesicity parameter. Sorry to change names. It's the same. So this parameter, we can write it down in terms of our variables, and it has this form. So at this point, well, it just, okay, it doesn't look very illuminating. However, what we found is that at the fixed points, which is the important thing, the parameter simplifies and takes this super simple form. And in particular, we notice that, well, it is independent of this x2, y1, y2. Now, x2 is associated to the kinetic energy of the suction. And on the other hand, these two variables are associated to the potential energies of the scalars. Now, although it's independent, one really needs to check at the fixed point whether or not the fixed point, and this is actually physical, but the expression is very simple, and we immediately see that if we want to find non-geodesic fixed points, beta cannot be zero. So beta equals 0 means a geodesic, and there's nothing to do there. On the other hand, because the variable here, as we saw from the Friedman constraint, or one can see from the Friedman constraint, this variable is constrained to lie between -1 and 1. Therefore, the magnitude of the turning rate parameter, or this non-geodesicity parameter, is determined fully by this beta, which is again associated to the derivative of the free space metric. So this again provides a very simple way to identify these trajectories. So we studied the case where these these parameters are constant, which means that the kinetic and potential couplings are all exponential. The system is a 6-dimensional system. You don't have to really look at this. So at this point, what we want is to first look at the phase space. So we need to find fixed points, their properties, and then the stability. Now, again, for people who are more have worked or have seen this, this may be familiar. So we find sort of standard fixed points associated to when you have a scalar with a fluid. So fixed points in this case are what are called kinations. So it's a point where the kinetic energy dominates, in particular, in this case, for this axion. Then there's a point where the fluid itself dominates. Then there are the solutions, which are again common in exponential quintessence models, for example, which are called scaling, where the kinetic and potential energy of the scalar are both evolving. And even though the equation of state for the total system, including the fluid, behaves as if it was dominated by a fluid. And then there is the most famous, the scalar dominated, which is a typical point that gives you acceleration in quintessence. So these are kind of standard. We find also a few more new points, and in particular, new points associated. Oh, sorry, I didn't say here, but the non-geodesicity parameter is 0 for all these points, as well as for this one. So these points are interesting, but not what we are looking for. So there are these other points which are kind of equivalent to the previous one, kination and scaling and scalar domination, but are really coming associated to the axion and the axion-axion system, the fact that we have a coupling and the second field. So these are kind of more standard, and again, all are geodesic. And finally, we come to the most interesting one. So there is one multi-field kination where the kinetic energy of the axion and the saxion dominate. That is a geodesic point. So in principle, we don't really care. We're not very interested, but it's a new point that arises there. And on the other hand, we have these non-geodesic fixed points where the geodesicity parameter is non-zero. So these are the points that we were looking for. So they do arise and are given by this. So W again takes a very, very simple form. Okay, so the next step when you are analyzing at this kind of situation is to look at the stability. So here I'm just going to summarize for the other points that are more standard, the stability properties are very analogous to other examples. But here, so these are the two more relevant new points. So this multi-field kination point, remember this is geodesic, is always unstable. Okay, that's fine because that's something that will happen in the past. But more importantly, again, we were looking for non-geodesic fixed points and their stability. So if we look at these fixed points from the global point of view, so including all the variables, what happens is that they are unstable. However, if we just focus on a submanifold, sorry, I'm going to turn on my lights. If we just focus on a submanifold, in particular this one, they happen to be spiral attractors. So I will show this in a moment. Sorry. Apologies. It's not seeing anything. So in principle, this will be interesting. Unfortunately, they are not globally stable. They are only stable in a submanifold. So what does this mean from the point of view of realizing a cosmology with this idea of having these non-geodesic points evading, if you want, these Swampland constraints? So here I have, so we have an example of how a trajectory will look in the sub-attractor case. So here I fixed these variables to 0. You cannot turn on even a tiny bit because otherwise these points are not stable. But if we stay at this sub-manifold, then these non-geodesic points, one, can arise, are attractors, and also allow for acceleration. So here the yellow region is a region where I can have acceleration. okay? In particular, W effective or the W total is given by this, so it is indeed accelerating. The non-geodesicity parameter in this case is 9.3. And in this, so I plot two examples. In one example, the trajectory goes from kination through a scaling point, one of these scaling solutions that some people also studied in the past. And then it goes to the non-geodesic point here. Another possibility is to go through from kination to the fluid point, then pass through this scaling and eventually going towards the non-geodesic point. Now, these solutions, these paths will be realistic, but not quite, because of course this is just because I'm forcing the system to stay in the submanifold. So obviously we won't even be able to get anything realistic with the full system. So this is the sort of the power of analyzing this using these dynamical systems. So, okay, one may now ask the question, so can we have something more realistic? So here again, in this previous example, I focus on exponentials, but if we are thinking about an axion, exponentials are not really what we are interested in. So using the techniques, the good thing is that now we have all the tools to explore something beyond that. So we explore an axion monodromy-like model. The system becomes a little bit more complex. There's one more variable. But so the remarkable thing was that some of the fixed points disappeared. Okay, so these are geodesic fixed points, so maybe it's fine. We don't care much about that. However, the non-geodesic fixed points also disappear. So there are no non-geodesic points for a system where we have an axion monodromy-like model. So obviously this is probably not the end of the story, and we are exploring more using these techniques. So let me just mention very quickly coupled scalar sectors. So what we have seen so far is just use the axion system as purely dark energy, but clearly since axions are very good candidates for dark matter, the obvious thing is whether one could use the axion system as dark sector, with the axion playing the role of dark matter and this axion the role of dark energy. There have been quite some work on this since some time back. Again, we wanted to explore more in detail what the kinetic and the potential terms are doing, and whether this could be disentangled. So again, what we did was mentioned also in a previous seminar. So let me just mention that while we explored this a little bit, what we found is that very nicely, this system can be written in terms of an interacting vector, which is something that arises in interacting models. So this in principle also allows to identify the different roles. However, what we found is that at the level of the background evolution, the kinetic and the potential coupling are degenerate. So what we are exploring now is how to disentangle this at the level of the perturbations. Okay, so here I just come to the final part. Okay, so the idea here is that, well, scalars abound in string compactifications, and they usually come in pairs, in this kind of pairs. So essentially they come as a complex scalar with the roles of the real and imaginary parts very well identified in terms of geometric moduli or fields coming, or axions really, coming from these P forms. They allow us to at least get some ideas into the challenges that need to be addressed for dark energy. Not only in the case of the single case, but also as axion multi-field models and hopefully non-geodesic trajectories. So far, we didn't find something very promising, but yeah, we are trying to explore something more there. And again, this can play very naturally a role of a coupled dark sector. So I just want to mention also this work where we actually looked at a more concrete stringy model in an heterotic orbifold. This is just a toroidal compactification. Here, the only message I want to give is that in this case, we had many of these scalars. In particular, we have 2 pairs of axion-axion. And what we found is that the structure of these kind of models, stringy models, give rise to sort of a landscape of unstable de Sitter extrema with very nice structures. And of course, here realizing a kind of multi-field saddle quintessence becomes clearly, I mean, it does work, I mean, it's fine. So something we explore as well. And so something we are exploring now is, so I did not touch on the phantom or mirage phantom that can be also explored, something we are exploring at the moment using precisely these scaling solutions, because there also an effective phantom behavior can arise. And the other thing is that we are trying to use some machine learning techniques, specifically symbolic regression, to try to get some the best potentials using sort of theory informed, if you want, symbolic regression, to get what are the best potentials and equation of states for dark energy that are also consistent with observations. So that's where we are now. So let me just conclude here. And of course, if there are any questions, please go ahead.
Thank you so much. Thank you. Very nice talk. There are any questions?
Thank you very much for the nice talk. Yeah, my question is simple, actually. I used to hear always that scalar fields are motivated from, this string theory, supergravity, etc. I'm wondering, it's like in quantum field theory, we can argue that, just from the representations of the Poincare group and constructing and interacting theory, you can have scalar fields like naturally.
No, that's fine. But so if we want to say, well, I'm going to consider string theory as my, if you want, my consistent theory of quantum gravity that perhaps I can use as a tool to construct something more realistic, then I cannot avoid. So it's not that I want to get scalars, it's that I cannot avoid it, because we have to start from 10D and come to 4. So there's no way to avoid having those scalars. So it's not that I want to have these scalars, it's if we are going to consider this as a possibility, there will be many scalars, and I know what kind of properties they can have, what is the origin, etc. So obviously, if you say, yeah, but I don't really think that's the theory, then they will come from other, as you are mentioning, they will come from other places. Mm-hmm.
I see. Thank you.
Yeah, that will be the idea. Mm-hmm.
Thank you. And Florian?
Hello, Ivonne. Thank you for your presentation. I have 2 questions, in fact. So the first one is, I didn't quite understand why you use the hilltop model for inflation, whether you have D-brane inflations, which is strictly from the string theory potential.
Mm-hmm.
And the second question is in slide 31. So you show the equation for the cosmology, and then you are not showing the continuity equation. Are you violating any energy condition here, or?
Yeah, no. So let me go to the
Thanks.
first question. So very good. Yeah, sorry, I went a bit fast. So, good. So, let me put it this way. Let's suppose that we accept this. Let's just suppose that we accept these constraints.
Okay.
Yeah. So if I say, yeah, okay, this is true, this has to be satisfied by my potential, I accept them, then you can immediately see that these kind of situations are possible.
Yeah.
Yeah. Not all of them, because they need to be such, so they need to be unstable or saddles, but sufficiently unstable because this is a parameter, this is a number of order 1 with a minus. So obviously, say is -2. So it has to be really like unstable, right? I don't know if you see what I mean.
Yeah.
So basically my point is, okay, so if we accept this is not possible, these two are possible. Let's consider what kind of unstable de Sitter I can have. And so here I did not really was focusing on brain positions, but more specifically on geometric moduli. So from that point of view, yeah, these geometric moduli. Okay. So an axion is a clear, no? An axion is very clear. So this will be hilltop.
Okay.
So the axions that come from string theory and really from anywhere, because it's just a cosine. So naturally they have the hilltop by themselves. So axions, you may say, well, that's axion, that's nothing new. But actually what happens is that when you look at these fields, geometric moduli, for example, a modulus that is describing the size, let me say the size of the full manifold, for example. You can compute, or the size of some of the part of the internal manifold. You will have situations where those fields, when you compute the potential, it may have this form, for example, and this potential has this hilltop here. So your question maybe is, well, but this is a little bit, I mean, why should the field start here and not at the runaway? So actually what happens for this particular model is that, this potential, sorry, is that the runaway is too steep, but the hilltop, okay, in some way, since we have that this is too steep, this perhaps it's a little fine-tuning, but it's a possibility that I can have. And actually what happens, we summarize many, no, sorry, not in that way, but we summarize many possible hilltops that come from supergravity model. And you can sort of explore that those hilltops will be indeed sufficiently unstable to satisfy the Swampland constraints, and also can drive acceleration. So yeah, in a way, these actions often have this kind of hilltops. And in the model that I mentioned with heterotic orbifolds, actually we only have saddles. There you have saddles, not quite the full hilltop, but many saddles. And they all satisfy the Swampland constraints. So this is like very, very, actually very common to have this kind of hilltops for this geometric moduli. So that's kind of what happens often. And the other question, very good. So the continuity equation, sorry, it is there, definitely. So there's no violation of energy conditions at all.
Yeah.
Yeah, I just did not write it, but it is there. So,
Okay. Thanks.
yeah.
So let's thank Ivonne again. Thank you for the very nice talk.
Thank you.
you.